So now that you have an idea what a map does in general, the first type of map we'll talk about is the tree map. It's not to say it's more important, not to say it's more interesting, just the first one we're going to talk about. So the map is all about how do we search into the data. And when we add something to the map, the first thing we have to do is find that shelf. So you think of it as a library. You return a book to the library. It doesn't matter if you have 1 copy or 10 copies of said books. It doesn't matter if when you put that copy over, you take off the other one. First thing you have to do is find the shelf it's supposed to go on. And so the simplest way to find something, simple as far as just logic goes, I just start at the front of the library and I keep walking down the shelves till I find the place where it's supposed to go. That's also the slowest way to do it, but it's the simplest way to do it. So really, Java is smarter than that. There's 2 primary ways we get to that. And the tree map is probably the quicker way to be able to break up the list as far as your understanding goes. So think of it this way. I have a deck of cards, and I want to find the Queen of Hearts. I can go through the cards one at a time, and at most I'll have to go through 52 cards in order to be able to solve where that Queen of Hearts is. But what if I could take my half of the deck and give you half the deck? Now, if we each look through it, at most either one of us has to do is look through 26 of the cards. So that theoretically gets us at least half the time on average. I mean, it could be the first card, but it also could be the last card. So between the 2 of us, there's 2 of them there. Well, if we split it half again, if there's 4 of us sitting here, then all of a sudden that most each of us has to look through 13 cards. So that's the strategy that we're going to look at. But again, we don't need to look at them all at once. What we can do is essentially create this tree, if you will, ranking the objects. And we'll see how we're going to do that here next. But in order to do that, we have to decide which object is greater than or less than some other object, which is a bit of an arbitrary decision. So the way this structures then is we look at a tree. We start with this tree map object. And the first object that goes in the tree map becomes the root object inside of there. So in this case, let's say we're putting numbers inside of there. Keeps it easy. So we put the number 44 inside of there. That becomes the root of the tree. Well, when we added another object, we make a decision, is that new object greater than or less than? So in this case, we added the number 67, which is greater than 44. So we add this to the right of the tree. So again, the tree bisects all of my data. Bisects meaning there's 2 branches. So when I added another object inside of there, we say, okay, is that greater than or less than 44? Well, it's greater than 44, so I'm going to add it over here. Well, is it greater than or less than 67? It's greater than 67, and there's no right to that, so we're going to add that to the right of that. So at this point, we just have a list. I mean, it's not very interesting, but it's based off the fact that we put these objects in this order. Well, what actually happens inside of a tree then is we don't want a list because that's slow to look through. What we want to do is what's called balancing the tree. And so what we want to say, and there's a big algorithm that makes this happen that's not part of what we're studying, is we want to make it so we have a root in the middle that has equal numbers of things on the left and the right. And so since there's 3 inside of here, we want to make sure that the left of the root is less than and the right of the root is greater than. So the tree becomes this root of 67. And then to the left of it's 44, and to the right of it's 88. So the point of it is as we're going to go searching, do you have the number 44 inside of there? I don't have to go look through all 3 values. I look at the root. If it's not 44, then I can cut it in half and say, okay, well, it's going to either be the left or the right. It's less, so it's going to be the left, and so there you go, 44. And so as the tree grows, you can see the root might change. In this case, we've gone back to that 44 value. And it's really dynamic what's the root. It's not important exactly which one becomes the root. What's important is if I say, do you have the number 33 inside this tree? I search the first one. Are you 33? Nope. Is it left or right? It's left. Are you 33? Nope. It's left or right? It's right. Boom. Are you 33? Yes, I am. So in 3 searches, I found that this exists, or maybe it doesn't, as opposed to having to look through 1, 2, 3, 4, 5, 6, 7 potential objects. So I've cut my search time in half, guaranteed, for what's going on. Could be quicker, but this is what's called an N over 2 search. At most, I have to search half of the objects that's going on inside of my map, inside of my tree, inside of here. So the way this works then is the tree map has this thing called a map.entry. And the entry is what represents the value that goes inside of it, and then the entry has a key and a value that goes with it. And so the key is any comparable object. We'll talk about what a comparable is just in a second. But it's basically something that I can say is something greater than or less than inside of it. And then the value is whatever else I want to store inside of that. So the tree map is made up of a bunch of map.entry objects. That's an interface that's part of the map that's out there. And so when I look at it, the map starts at the tree map, and I say, do you have this inside of there, or do you want to add this inside of there, or do you want to remove something inside of there? Basically, most of the map operations look through and do a table scan, if you will. Let's go search through all the objects, and then it searches, and these guys jumping either down the left-hand right branch or the right-hand branch, depending on how many items are inside of there. It grabs the appropriate value, or tells you that's not the map, or it adds the appropriate value, and all the stuff that happens internally. Now, the mechanics of a map is beyond what we're trying to teach here. It's important to understand it, though, because you have to understand the value of comparing inside of there. Once I understand greater than or less than, I can dramatically improve my strategy for searching through this. And so when I want to compare two things, numbers is easy. I know what greater than less than looks like numbers. How do I compare two strings? Well, I can use alphabetical order. That makes sense. But how do I compare if one ticket to a show is greater than or less than another ticket to the show? Maybe the price? How do I compare if one person is greater than or less than another person? We need to find some way to be able to compare it. And eventually we're going to come down to something pretty simple like a number or a string comparison, but we need to define it in Java as what's called a comparable. And so the comparable is an interface with generics that says, hey, I can compare one object to another object of the same type, T being type inside of here. So I can compare two product objects. I can compare two customer objects. And it will return back to me a 0 if they're equal, a negative number if they're negative, if they're less than, or a positive number if they're positive. And so we'll see this code at some point, but for now, just know that this interface is out there. There's also a comparator interface, which takes two objects and does the same thing. So you can either say, I'm one of these things that's comparable, so you can compare me to my peers, or you can have a third party that says to compare these two things. So I could say, which one's the greatest, basketball player? Well, I can compare one basketball player to another, and there's one criteria, but I can have an external criteria that could say, okay, well, is it college or is it pro? I mean, so we could say Michael Jordan was the greatest basketball player of all time, pro, but maybe college we would go with Magic Johnson instead. Certainly LeBron can't be because he never played in college. So that's the idea. So you can have different rules implemented different ways using these different interfaces. So the advantage of the tree map then is it grows very gracefully. As we add in items, they just basically get tossed in the map and it just gets bigger and bigger and bigger. We don't have to reallocate data storage. It just automatically sorts the data for us and keeps growing. Compared to the hash map, which we'll see in a little bit, it's very slow looking it up because at most I search. At worst, I search half of the items. The hash map can do much better than that. You could be lucky and find on the first one on either one of them, but on average, it's slower than the hash map. And I then must use the comparable or the comparator interface in order to be able to use a tree map. So that's the tree map. It's really quite graceful because, as I said, the biggest advantage is you're sorting it as you go. If sorting is important to you, tree maps are great. If they're not, there's a little bit quicker way, which is the hash map, which we'll look at separately next.